So welcome everyone to Support Vector's weekly research paper reading session. Today we are reading actually one of the seminal papers that landed on literally Jan 1st, the New Year's Day, early in the morning. And the moment it landed, I recall getting multiple messages from people saying, hey, something big has dropped. When can you explain it? Well, now the time has come. I took some time out to study this paper, and I am going to explain this paper in a sense-making way. It is rather dense. It speaks of many things, and it is really worthwhile unpacking the things that it says. The title of the paper is mHC, Manifold-Constrained Hyper-Connections. I'll do this paper in a few iterations. First, from a impact perspective. What really is the impact of this paper? If you look at the YouTube, there are statements that are somewhat hyperbolic that say transformer has been reinvented differently, or I don't know, some profound thing has happened. At the same time, when you look into what is the big change, the explanations are broadly correct, but I felt that they lacked a bit of depth in unpacking what is in here in the paper. So I'm going to explain this paper using very simple two-dimensional vectors and analogies. Is this a significant breakthrough? Yes. In transformers and in every neural architecture since ResNet, there has been the concept of residual channel. That residual channel has been a signal pass along. Input, keep the input to a layer and add a little bit of what the layer does to the input as a superimposition or as a perturbation, additive perturbation. To do so is the residual thinking. What it does is it doesn't replace the original signal entering a layer. It instead modulates it, makes small perturbations to it. It turns out that to do so is a very good idea for reasons that we will go into. This has been there for more than a decade now since rest. That residual channel has remained more or less untouched, though various efforts have been made to see what you could do with that channel. More recently, I believe it was the Alibaba group that did a precursor to this paper, which was called hyper-connections. What they did is, instead of making it a one signal being propagated along the residual channel, they split it into 4 signals. And those signals could mix and match. A common metaphor you hear on the internet these days describing that is a 1-lane highway has become 4-lane highway. So more traffic can go through. I'll actually argue that that's not the right metaphor. It is not that more traffic can go through. It is actually something slightly different, but that intuition is not too far off. It does have quite a bit of a grain of truth. I'm going to use a different intuition to explain. When the precursor paper went with it, it turned out that it lacked certain control elements, some things that led to unexpectedly bad behavior. For very deep networks, it would lead to exploding gradients or vanishing gradients or signal amplification, excessive signal amplifications, and so forth. So that one way to think of it is, imagine those of you who are from signal processing background, imagine creating an amplifier, a sound amplifier in which there is no feedback loop. As you can imagine, it can cause the sound to quickly shoot up to saturation point. So you need some way to prevent ungoverned growth. This paper brings about that sort of a regulatory regime onto the residual channel with its hyperconnections, with its so-called 4 lanes. And why this matters, one would have said, okay, this is a minor correction to our prior work. Why this matters is actually quite interesting. It matters because these people, the key contribution that they brought was not just that they governed it, they controlled it, they made the thing possible in a controlled manner. It showed that the results are much better than a baseline transformer with a simple or a vanilla residual channel. They also show that all the pathologies of the prior efforts are gone. But more importantly, what they show is that the compute cost doesn't go up, the memory cost doesn't go up significantly. It goes up by a factor of just 6 or 7%, which from a breakthrough perspective is nothing. Imagine getting a significantly better transformer, a significantly better LLM that does state-of-the-art results on benchmarks for a, for without bloating the size of the model. Right? You're not increasing the size of the model. You're just changing its geometry. And that's a paper that they make. That's a point actually that they make very specifically. They're saying that their contribution goes to the topological architecture design, the macro thinking about how the transformer itself should look like. And by making a breakthrough at that level, you get another axis of neural scaling. You get better performance not just by making the model bigger, but by changing its topology, by changing its structure itself, structure itself. And that's, as I say, it suggests promising direction for the evolution of foundational models. So with that background in mind, I will give you two aspects. Is the concept of residual connection familiar to all of you, or do you think I should give a very quick? I should give a very quick. Okay, I'll do that. Just as a show of hands, you go ahead.
I would definitely could use that. I do also have a question on the same topic. For ResNets, are most of them are most ResNets are part of LLM networks today, right?
Yes, actually, another way to put it is modern day neural networks are almost never made without residual connections. ResNet showed the importance of residual channel, and the rest was history. In other words, everybody went about and retrofitted residuals into their whatever architecture they had. And transformer is now itself, right from the very first version onwards, there was always a residual channel. So to make another, I would call this the next big breakthrough when it comes to the residual channel. So let me read through the summary of this paper. And what I will do, the way I'll unpack it is, I'll unpack it using a simple physics analogy or a physics metaphor. Recent studies exemplified by hyperconnection, HC, have extended the ubiquitous, actually, I'll do it here. Recent studies exemplified by hyperconnections have extended the ubiquitous residual connection paradigm. So this goes to what you asked just now. It is ubiquitous. It's everywhere nowadays. A connection paradigm established over the past decade by expanding the residual stream width and diversifying connectivity patterns. One thing you'll notice in this paper, the language is dense and the sentences are long. While yielding substantial performance gains, this diversification fundamentally compromises the identity mapping property intrinsic to the residual connection. That, of course, makes you wonder. So there are lots of terms here that I would, unless you guys say you know it very well, I will take the liberty to explain it. Is that all right? There's compromises the identity mapping property. What in the world is this? We're going to deal with this. So we will say the extended or ubiquitous residual connections. So what are these? I'll explain this also. Okay, to address these challenges, we propose manifold-constrained hyperconnections. Well, a manifold is something that also needs explanation. And what does it mean to say manifold-constrained hyperconnections? A general framework that projects the residual connection space of HC on a specific manifold to restore the identity mapping property. Now, if you don't know what residual is, what you don't know what identity mapping is, and what what in the world this manifold is, no, let alone manifold constraint, this might be a good time to say, okay, let's go for a coffee break. So, while incorporating rigorous infrastructure optimization to ensure efficiency. So as you can see, I'll just simplify this whole thing in this. What they are saying is there is something called identity mapping property on the residual connection, the side channel, which it is important to preserve. Why it is important to preserve, we'll see. And one way to preserve it is to do something called manifold constrained. Put a manifold constraint on the hyperconnection. So what is manifold constraint? I will come over this in greater discussion, but here is a simple way of looking at it. Imagine that you have a blanket, right? So, and the room is very cold. Would you not like to make sure that you stay within the limits of that blanket and inside it, right? So the fact that you are limiting yourself to the territory that the blanket affords can be said in a fancier jargon by saying you're ensuring that you are manifold constrained. Right? In other words, you stay within the limits of certain surface or hypersurface. A manifold is sort of a well-behaved hypersurface. I hope that is it. And they're going to somehow use this notion of manifold constraints or staying within the perimeters of a blanket to solve the pathologies the prior work brought in. So prior work brought in multi-lane in the residual channel, but it led to all sorts of pathologies. And somehow some concept of staying within the blanket is going to solve it. And we will see how that happens.
So, like, you think of a blanket on top of you, and
Yes.
you could map that to a Euclidean space, right? So I'm curious in this sense, how what does the like Euclidean space look like when they're talking about a manifold, or maybe there isn't one at all? Maybe it's more theoretical or something like that.
Yeah, so in this paper, today I'll take a lot of time to unpack this paper because it is important. But let me answer your question. See, think of a blanket crumpled up lying on you. Now imagine a little ant on the blanket. Now, to you, looking at the blanket in the ambient space, three-dimensional space, Euclidean space, it looks all curved, isn't it? It is filled with ups and downs and curves. But to the ant on the blanket was initially flat and still locally flat, isn't it? So you say that the blanket is actually a two-dimensional surface because the ant can move only backward, forwards, and left and right, or some combination of the two. It remains a two-dimensional surface that to it looks flat locally, but to you doesn't look flat because you are seeing it in the ambient space, right, or the embedding space. Does that give you the correct picture? So we are saying, imagine that somehow these guys are going to put an ant on a blanket. I think that's a more accurate metaphor. But telling the ant, do not go outside the surface, the limits of the blanket. So that is the literal meaning of manifold constraint. We are making the ant or the solution to be manifold constrained. And they're saying, and this is the big part which they are doing, they're saying that while incorporating rigorous infrastructure optimization to ensure efficiency. See, this is the trademark of DeepSeek. From their first breakthrough to now, what they are achieving is not better language models through scaling, making it bigger and bigger and bigger. They are actually, in almost all of their papers, finding a way to make the current size large language models better. And that's what they focus on. They're saying they're going to bring about the improvements of hyperconnection while while incorporating rigorous infrastructure optimization to assure efficiency. So this paper is, as much as it is about this new idea of manifold constraint, it is also a bag of tricks, very clever tricks to make sure that you don't pay the piper. You don't pay in infrastructure overheads or in compute overheads or memory overheads. The cost is marginal, just about 6-7%. So you get a substantial gain in model performance for a marginal increase in cost. That is what the paper is all about. And it is very much in the DNA of DeepSeek. Empirical experiments demonstrate that mHC is effective for training at scale. So they make the point that scalability is not lost. You can train mHC, this architecture, at scale, offering tangible performance improvements and superior scalability. So those are big claims. As it would turn out, each of the claims are true. We anticipate that mHC, as a flexible and practical extension of HC, will contribute to a deeper understanding of topological architecture design and suggest promising directions for the evolution of foundation models. Of all the things in the abstract, the last sentence is the most telling. What they are saying is it's practical, it works, but that is not it. It will contribute to a deeper understanding of the topological architecture design. What should be the macro design of neural architectures itself, and how we can focus on that to create the evolution of foundation models. That is their thing. And like all great papers, is not only do they make a breakthrough of significance, they open the door to a lot more breakthroughs. That's what this paper is about. So now this paper goes on, but if you will allow me, instead of going through this paper's mathematics, which can be a bit dense, I will give you the exact same mathematics, but should we say uh, in a simpler language, okay? A little bit easier to make sense of. Okay? So let me go and do that.
While you're pulling that up, I just have a quick question. So is the claim of this paper not only does it converge faster because they're using tricks with the manifold, but that you can have as much data with less storage? Are those two correct? Just curious.
Both things. See, first of all, a convergence, it is not about convergence, but stability. A lot of the pathologies of the prior efforts are gone. They fix it. It, of course, with lesser number of iteration, it does converge in that sense that it achieves uh, the loss function plateaus sooner. And it does not compromise scalability anywhere. You can see if your mantra is, I will make a bigger language model using more parameters, scale it up, then that access still remains with you. You can use that access as well as this geometry, this topology of the network. And you can have the best of both the worlds. You don't lose the other side. That's what they're saying. So what are residual connections? See, suppose you have an input layer, and at this moment, let us not worry too much about what it is. Suppose I take a layer and signal, no, let me go. Okay, signal. So let us say that this signal goes in. Normally, when you think of a neural network, you can think of a neural network as a function, right? It has certain weights in this layer. So it's a function of this layer, so that what comes out of it is XL plus 1 is some function of XL, right? Given the weights. The shape of the function you control through the weights by changing the parameters of the layer. So far, so good, guys? This is your basic understanding of it. Now, the idea of residual is that take a bit of the original signal and bypass and add it also, right? So if the original signal comes back here, then what happens? It becomes, so this is FXL WL. So both of these need to be added now, isn't it? Now, why would you want to do that? Let us say that you are looking at a deep network. What is each layer supposed to do? Each layer is supposed to learn a better representation for solving that problem. Let's say you have to tell the cats apart from the dogs, right? The input data comes in a raw data manifold, Now you keep transforming that manifold. You come up with different representations so that in some representation, it is far, far easier to tell a cat apart from a dog. Am I making sense? That is what layers do. They learn better representations. But let us say, so the hope is that Excel, this is a better, like a better representation. It is a better representation. And for it to be a better representation, if you do, let's say that without residual, it would have just been Excel plus 1 is. But these two equations, let me call it number 1, and this is number 2. With residuals is number 2. Right? What is the change that happens when you add residual? See, in number 1, in this particular example, it is a replacement. XL plus 1 replaces XL as the signal moves forward. You're saying, I'm going to do a radical change to it. I'll replace the original representation with a completely new representation. But if you look at the number 2, what does number 2 say? That is where the clear important distinction is. Number 2 says, I'm not going to replace the input signal to the layer, but I'm going to add a small modification to it, right? So that the representation gets better. Is it making sense, guys? Right. I'm going to layer over it something better. So here is one picture that I have in mind. Take it very lightly though. Those of you who do Photoshop or image processing, what do? You have a base image and then you put a mask and you put a layer over it. Now, when you start doing Photoshop, naively, you edit the base layer itself. The problem is, you can't see the differential effects, what each layer is doing, right? But by doing your changes in the next layer and imposing upon it, it is an additive effect upon the base. Residual connections are exactly that. They are saying, let the input signal propagate, but add a modulating factor, add a perturbation term on top of it that improves the representation, right? So this opens the door. The reason residual connections in hindsight, everyone realized that, great ideas when they come, everybody hits their head and says, why didn't we think of this before? Right? And I'll give you an analogy. Let us say that you have a 100-layer deep neural network. Let us say the 57th layer has already figured out the best representation to solve the problem. If you take approach 1, that very good representation has the risk of getting lost, right? Because you have so many layers coming after it. The subsequent layers, they better be clever enough to behave like identity functions. Right? People realize that making deep layers was hard. But the moment you bring in residual connection in a 100-layer neural network, let's say that the 57th layer has already figured out a good representation. Guess what the rest of the 58th to 100th layer, what will their F functions be? They will be close to 0, right? They would add no modification to the understanding because they will understand that the representation already is very good. They have nothing more to add, isn't it? So it gives these layers the ability to say, this is good enough. I don't need to touch it. Whereas without residual connection, they have no choice but to touch it because signal can only go through them. Right? There is no bypass channel. Do you see that? And that is why, but see what happens is you can never tell at which layer the best representation would already get generated. So you can make deep neural networks, very deep networks. What residuals made possible are very deep networks. With the safety that if a good representation is discovered early on, no harm done. The rest of the layers will just give you identity Like we'll let the signal propagate as is, and they will have vanishingly small effects, right? The perturbations they cause would not be harmful, right? They will essentially look like transparent glass, isn't it? They do nothing, and signal
Yeah.
is passing through. Yeah.
Sorry, I have two questions. One is, do these, so do we always, this all makes sense, but do we always pass the, uh, what do you say, the input, the XL input as it is, or do we make sometimes in some architectures, we make modifications to it and then pass it to the next layer in the skip connection?
Yeah.
And
Dishant, the
yeah,
classic residuals that has existed in most of the dominant architectures, they are a signal pass through. They take the input and pass it as is to the output of the layer. Right?
okay.
So, but there has been a body of research, prior research, which has asked, hey, what happens if we change it along the way? Most of those efforts were actually not terribly successful, which is why you don't hear of it. Like if you unpack any of the large, big transformers or language models, you will notice that they're just doing simple pass through, simple bypasses, residual connection. It's just letting the signal hop across the layers. The
Yeah,
input signal simply hop across. Or simply put, they give you identity. The formal word you use. Remember um, in the abstract, we came across this big word, identity preservation, or something like that. That is it. The channel acts like multiplying with the identity matrix, right? So in other words, signal goes as is. That is the good thing about it. Now, this was the residual. So guys, do we understand residuals now?
yeah. I just have one more question. Can I ask that?
Okay, sure.
Yeah. I mean, how do they decide that where exactly to put these residuals? In transformer also, I think it is at some places only, right? Not all places. So how?
Oh, look at the transformer architecture. Let's go back to the classic transformer. Since you raised this question, it's a good question. Why don't we go and look at attention is all you need? The original transformer paper, right? Let's look at the images because we don't need to go to the full paper. The images have all of these. Okay, which will be the good image? Let's take this guy. Where is the image? Visit. Let's look at this. Okay, I'm going to look at this. Okay, look at this. You see that one transformer head here is multi-head, this one, this block. It signal goes in, KQV goes in. You see that? It's going in, it is, multi-head, many of the heads, but simply put. But do you see this channel? Let me see if I can color it or it will allow me to color. Well, no, it's not allowing me to color. Do you see
Yeah,
these
yeah, I can
arrows?
see that. Yeah.
Yeah, they are all over the place. Do you see that?
Yes, yes, yes. No, but my question mainly was, it is on the outer layer, right? Inside there, the multi heads, and inside the feed forward. Uh, so
No, no,
there
it
we
is
don't
around the feed forward. See, it
around.
has to be around a layer. It cannot be
Okay, okay.
inside a layer. No, by
Because
nature,
feed forward itself has many layers, right?
yes.
So
No, no,
so there we
one
don't
layer of
use it.
feed forward. Sorry, let me be very clear. One layer of feed forward. So there are two ways of doing residual. It's a good point, actually. Let me put it this way. See, I'll give you an example. Suppose this is a layer, one layer. You can do a bypass around one layer. You can choose to do. Now, this layer could be anything. It could be feed forward network. It could be attention network. It could be a convolutional layer. No, it
Yeah.
is your choice what it is. You can do that residual. Or you can see it has to be just be a geometry preserving transform. In other words, if the signal, let's call this X A, and the signal that comes out is X out. Let me call it X input, right? So X in, X out must belong to the same dimensionality. Otherwise, you can't add it. Otherwise, you cannot do a residual here. Because to
Understood.
add to signal, so long as the dimensionality matches, right? you're
Mm.
fine.
Mm. So basically, as long as we are doing a macro operation to something,
Yeah, yeah,
and which preserves the macro transformation, we can say, right, in a way. And okay, yeah, makes sense. Inside
yeah,
the network, there would be dimensionality changes, right? Because at layers over there.
yeah. See, think about it this way: each layer is a morphism. Um, it sort of transforms the signal, morphs the signal. Let me use the word morph. It morphed the input, morphs the input signal, isn't it? So, suppose you have multiple layers L1, L2, L3. What happens is you have some morphism in the first layer, some morphism induced by the second layer, some morphism induced by the third layer. These morphisms are composable, right? In other words, you can always think, suppose this morphism or the transformation that it brings is F1, then F2, compose F3, right? Or actually, I should write it the other way around. Sorry. First, you have F1. On top of that, you impose F2. On top of that, you impose F3, three layers, right? What you're saying is that that is equivalent to a morphism F prime. So it is as though these three layers act as just F prime, isn't it? So you can say X out is equal to F prime of X in. Dishant,
Yeah,
is it
and
making sense to
yes,
you?
yes, yes, and the dimensionality is being preserved. So that is the idea.
Dimensionality preservation is important.
Yeah,
Yeah.
yeah,
Otherwise, you
yeah.
can't do residual around it.
Understood. Yes. Yeah. Thank
So
you.
are we? Yeah. Okay, guys. So do we understand residuals? See, residuals are the great workhorses. It has a lot of interpretation. And in one of the landmark work that Anthropic did in trying to understand the transformer architecture and attention, they considered residual to be the main channel in which the semantic understanding of the input is built up. The semantic representation gradually builds up. You keep adding those F terms, they layer meaning after meaning after meaning on top of the base, right? So so there is a lot of things around how what residuals do. It is also in practical engineering. If you talk to people who are actually doing applied AI for problem solving, most of them they don't know much about the residual. They think that yeah, it's something that is there as a corner story, but it is not. It's quite central. So see, the residual, it follows what I would call do no harm principle. Let me write it down as a principle. So let me coin some words. Do no harm. What is the do no harm? This is called the identity mapping principle. Means the residual channel input that goes in here is still the input, right? Whereas the only person allowed to make the change is the layer itself. All the morphisms are here. Sorry, all the morphisms are here. Do we agree that all the morphisms is in the layer itself, right? So this comes out as fxi of the weights, and so when you do this, what you get is x out I plus 1, the layer plus 1, is xi plus fw of the weights xi. This part looks okay. So the fact that you leave it implicitly, you leave the signal as 1. You don't straight up. This is called the identity preservation, the identity mapping principle. Map it, leave it alone, don't do harm. That's the basic intuition. So again, the basic intuition is that if you do that, then a layer's job is to just add small perturbations or a little bit more meaning, more texture to the signal flowing through, right? That's all it is. So now comes this paper.
I
This
just have one quick question. Sorry. Again, this intuition is making me to question that. So while doing this residuals, when we add this, are we saying that now what will happen is that the earlier layers will consolidate faster with their weights?
I don't even understand the question. Earlier
No.
layers will consolidate the weights. See, layers don't consolidate the weights through gradient descent
Yeah, what I'm trying to
flow
say is
towards the
that
right value, no?
yeah, what I'm trying to say is that because we are adding this preservation mechanism now, so the earlier layers will learn weights faster. They will
In a way
converge.
it happens. In a way it happens. See, what happens is there is a lot of mechanics happening here. The problem of vanishing gradients, what would happen is when you would make very deep layers, the then remember back propagation happens in the reverse direction. Maybe I'll draw
Yeah.
it out. Suppose you have many layers, right? Layers. Now, forward signal transduction happens like this, but the reverse signal, the back propagation of the gradients
Yeah.
happens in the reverse direction. What would happen is that a strong signal, a strong gradient signal, and by here it is approximately zero. Right? The gradients more or less vanish. Are we together?
Yeah.
But by putting residuals, what happens to the residuals? Remember, residual carries signal in the forward direction,
Mm-hmm.
but it also carries gradients. It carries the gradient. It gives you a path to move. The gradient also moves in the backward direction. So gradient never vanishes. Why? The gradient of the previous layer is passed to the gradient of this layer. Right? So suppose you have gradient is following across this layer and there is a residual connection. Right? So what will happen? Suppose I have a gradient here. Here there is a gradient. The gradient gets sent here also, right? To the previous layer also.
Mm-hmm.
So gradient keeps flowing back also through the residual channel. Because the gradient also flows back, one of the biggest problems that happened in very deep layers used to be that by the time gradient would reach the earlier layers, it would disappear or become too weak a signal. So the earlier layers took a long time to learn. Residuals solve that problem.
Okay, because the gradients are also being incrementally passed back in a fashion,
That is
right?
right. And so you have a pretty strong gradient signal going back. You don't
Okay.
you don't see its attenuation.
Okay.
Something I see as well is that how residual blocks work is it uses convolution, and then what it does is after it will add the layers to then return the residual mapping. And what I'm very curious about, and we'll probably cover very, very soon, is in those residuals and that convolution, how we're seeing a manifold in that.
No. This is the classic residual. There is no manifold. Think of
No, I
it this
mean
way,
like
guys.
sorry, I mean like for this paper that we're looking at, the
No,
name.
we're coming to this paper. Before we come to this paper, let
Mhm.
us be sure that we understand the classic understanding of the manifold, the residuals. So this is the classic residuals. Then we will come to this paper. Right.
Sounds good.
So I want to make sure that you understand what residuals are. So now that we understand residual, now not to this paper, but let's come to a precursor to this paper. What the precursor said, I think it was the Alibaba paper. Was it Alibaba or ByteDance? It was a ByteDance paper, maybe. One of you can cross check who wrote the hyper-connections paper. Was it ByteDance or was it Alibaba? Um, so what they said is, let this layer be layer. Hyper-connections. Right? So this is going. What they said is that, see, suppose, so you realize that X is going through, X of the layer is going through, and what you see here is also X of the layer. Why? Because implicitly, you're not modulating it. You're just letting the signal go through. Right? So they had a temptation. They said, let's do something funny. let us do this funny business. We will take XL and we will create 4 versions of it. XL1, XL2, XL3, XL4. Right? 4 versions of it. Now, you might say, why in the world would you do that? What is the core intuition that you would apply to do this? They said, well, most of these discoveries are made by hacking. What happens if I do this? What if happens if I do that? So bear along with me and then I'll give it a physical intuition. Then you say, well, you may break it into 4 signal, but which of these 4? So suppose I put some transformation matrix here. There is some matrix here. Originally, so in layer 1, so let me not put it as layer 4. Let me mark it as layer 1. Layer number 1. Layer 1. Layer 1. The first layer. What do you do? Replication. Replicate. Make 4 copies of the signal. So now, here is a picture that I have, guys. Imagine a fiber optic bundle that has 4 fiber optics. Fiber optic. Fibers. Fiber optics. Are we together? So the signal is now going along 4 fibers or 4 lanes. One of the analogies are found in the internet. People are talking about traffic going along 4 lanes. Right? The traffic analogy is actually not very satisfactory from the math perspective. But both of these let's carry forward. So what happens? You have 4 signals going through this. Now what they say is that whenever a layer happens, what comes out, so inside there will be a layer and then there will be a residual, etc. At the end of it, make sure that once again, 4 channels are coming out. Right? In the very first layer, you make it 4 channels, and hereafter, for any layer, signal always comes in as X layer 1, X channel 1, X channel 2, X channel 3, X channel 4, X channel, let me make it 4 channel signal comes. Now you say, well, what will I do with 4 signal? You say that 2 things. These 4 signals are your input to a layer, input to a layer. Are we together? Then you have 2 paths. Remember, now I'll write it as 2 paths. The residual path and the actual, whatever the actual neural net is, a feed forward network or attention or whatever it is, CNN or whatever it is, doesn't matter. In the case of a transformer, it will be the attention and the feed forwards, right? Language models. So what it says is you have an issue now. You have 4 signals, 1, 2, 3, 4 coming in, isn't it? You realize that 4 signals are coming at this layer. So what you do is, for this, you multiply it, you mix these signals up. So imagine there is a mixer. And what the mixer does is it creates 4 new signals to go over the residual path. Is it making sense? You take the input white signal and you use a mixer to mix them up and create 4 new signals out of it. But for this layer here, what you do is you actually collapse those 4 signals into a single signal. So you merge into a single. Let me use a different color. And let's use a different color. Signal here. So that is okay. This layer will produce its output. Does it make sense, guys? Layer output. Let me just call this output F. And let me call this the a signal that is from the merger, it will produce this. But now do you have a problem? You can't do you can't add these 4 yellow lines to a single blue line, can you? Isn't it? What you need to do is you have to somehow break up the blue line into 4 blue lines. Right? So you have to do another on ramp to the highway. You need to take the signal and demerger. Like, let me just call it reconstructor that will create 4 signals, 4 separate signals. Am I making sense, guys? And now what you can do, you can do a plus operation. How? You will connect the, like, for example, this 1, 2, 3, 4. So now this plus one of the, yeah, each channel you can add the signals. You can still do your residual business. Do you see that? To be able to do this kind of thing, now you may ask, why in the hell would I do this? Isn't it? Why did I suddenly bring up the mixer, the merger, the reconstructor in the whole game? And these are just plain matrices at this moment, but actually they're not just matrices. Internally, they have some tanh, sigmoid, activation, etc. built in. But forget about that. Think of them as mixers, mergers, reconstructors. Now you ask, why in the hell would I do this? And the answer usually to these things from engineers always is, why in the hell not? Right? Why not? Let's do it and see what happens. Right?
And so then, and then doing it this way, you get all these wonderful things. But I'm still very curious about the manifold part. Maybe I can't wait.
Right. So the thing is, it turns out it seems too irresistible. Why not? Let's see what happens. So when they did it, they got early results, and the results were promising. They found the hyperconnection paper, the predecessor to this paper, found that, oh, wow, it works. So what do engineers do when one of their hack works? They run and write a paper about it, that it worked. Then let others can carry that idea forward. So they did that. There was one problem with it, though. See, a lot of these methods are discovered by, why not? Let's try it. Right? And then when it works, you have this feeling that there is something happening here, very interesting, that needs to be understood. Right? So once they published the paper, others jumped onto it because, oh, there's improvement. They realized a problem. The first problem they realized is that it doesn't scale at all. It has scaling problems. Yeah. So the good news, the bad news. Good news. Better, of course, better than baseline transformer. In other words, the normal way of doing it, right? With a single residual channel. Better than that. So, hooray, that's a great deal. But bad news too came along with it. Bad news. It is the fragility of it. Does not scale. Scale well. Leads to exploding or vanishing signals. So what would happen is, on the residual channel, either the signals would entirely fade out, right? Or they would somehow become too strong, explode in quantity, right? And likewise, in backprop, once again, lead to exploding or vanishing gradients. And so you say, oh no. But there's a reason why this happens. on the face of it, the reason is very simple. Because you are multiplying a matrix now, what happens is you have a signal. What used to be XL plus whatever the neural network did in the layer, now you have a matrix. You multiplied it by, you mixed it up. You have a mixing matrix for that particular layer. Isn't it, guys? You have a mixing. You just put one more matrix there to mix the signal. And we'll just focus on the residual channel. Forget about the merger and the reconstructor. That's not so interesting here. You put it is called the residual, right? The mixer is called the H residual in the paper. Now what happens is, when you go a few layers deep, you realize that you are doing, in effect, the residual channel is developing a signal that is looking like H1 res times H2 res times H3 res. You see that, right? Multiplication. It is in the paper written as this symbol of multiplication, Hi up to layer of Hi, the residual layers. So far, guys. Yeah. Now the multiplication has a very weird thing. Let us say that each of the matrices for any one channel was always producing, multiplying it with a number just a little bit less than 1. Let's say 0.9. Right? What with multiplication? Let's say 100 multiplication. If you multiply 100 numbers, all of them slightly less than 1, what will you get? It will become close to 0, right? So the forward signal vanishes. On the other hand, if this matrix, for some reason on a channel, is adding quantity, just amplifying a little bit to the input signal, 1.01, or just tiny little bit, what will it happen when you multiply hundreds of those numbers, which are just a little bit more? It will explode, right? And so you can have exploding signal in the forward direction, right? Likewise, the same story goes with gradients. Gradient 2 is a signal. If the gradients are following this, they too get into trouble, right? So that is the problem with this algorithm, hyperconnection. So you say that, oh boy, we are in a bit of trouble. Good news is it works, but it just doesn't scale. So it is sort of a research curiosity at this moment, isn't it? We need to fix this problem. We need to keep the it works part, but we need to solve the bad news, right? And here is the intuition that will help you solve the bad news. So what you say is that, why is this bad? See, I'll give you the intuition, or the discovery you will come to. This matrix H is what I will call the evil matrix, because there are no constraints on it, right? The, the machine can learn any matrix it wants. There is no constraint on it. So the weights inside the matrix could be any number, right? They could all be greater than creating amplification or mute the signal down, right? It needs some governance. So I'll give you a good. So it is unconstrained. Like, do you guys remember? Those of you, how many of you come from electronics background and remember how a signal amplifier works? Why do you put a feedback loop there? Like, for example, when you have a signal X as an amplifier, why do you make sure that you put a bit of the output you feed back into the input to govern it, right? To make sure that growth is controlled. Yeah. Very similar thing we apply, or the logic applies here. So I'll make it very simple. Suppose you remember that after the primordial splitting, there are 4 channels, there are 4 signals in the paper, but let me simplify it down to 2 channels, right? So let us say that the light is coming. One channel is just, I should have used blue light. Let me use blue. Blue light is coming. And the other channel is red light, pure red. So there are 2 channels. One channel is pure blue, another channel is pure white. So the signal, let me just call it, let me call it X1. I should use a different color. x1, I can represent it as 1, 0. Is that correct? Full blue, no red. And x2, I can represent as 0, 1, pure blue, pure red. Does that make sense, guys? Now, let us say that the signal is made up of, they're equally strong, right? So equally strong means, let's say that they have 100 photons per second going through. So we will say 100 blue photons and 100 photons. Does that make sense? Now, let us think about the mixer. If these two things, the blue and the red go, and if you get this intuition, you'll get it, guys, what is being said here. The gist of the paper is something, a very simple statement. They are saying that, let's say that you have a mixer, and these are fiber optic cables coming in. Surely the number of photons should be conserved, right? Number of photons should still add up to 100. Does that make sense? Right. So let us say that on the 2 channel that comes out, you have, this would make sense, 70 blue, 30 red, right? Then 70 red, 30 blue. Does that make sense? Now observe what is happening. The rows add up to 100. If I write it as 70, 30, 70, 30, right? Then, red is, 30, 70. I apologize. 30, 30, 70. Do you notice something interesting? This is your mixing matrix, right? It is saying 0.7, 0.3, 0.3, 0.7. So what are you doing? You're saying you can take, like, if you can have channels with a mix of red and blue photons, but the number has to be conserved. Does it make sense? Across the 2 channels, the same number of reds and the same number of blues should be there, right? Am I making sense? Right. In other words, the multiplying matrix, their rows and columns must add up to 1. Yeah. So the mixer, let me call the mixer H res is equal to this. You must say that, and you can see that it will work out. If you multiply this matrix with 100, let's do that. H res times red. Red was what? 1, 0, right? Or 100, 0. The 100 red and 0, the first channel was 100 and 0, right? 100 red, 0 blue. Am I making sense, guys? Right. So this will become, if you multiply it, it will become 70. You work it out, and you will realize that you will get the right mixing values coming out from this. Right. 0.7, 0. Okay, my matrix may be a little bit off. Let me see how I worked it out as an example on paper. Okay, basically what I said is, let's take something simpler. Actually, in my example, I took half and half. So let's go with half and half for the time being. So because I went with half and half, yes. So yeah, you will see that this does come out to be 70. Okay, so this is correct. 70-30 also works. You can do a mixture, but to conserve the number of photons, would you agree that in this matrix HRES, the defining quality is rows and columns must add to 1. This is basically a conservation law of signal. Let me call it a conservation of signal mass. Is it intuitive, guys? The total number of photons should remain the same, right? You're just saying that the signal Mass should remain conserved. This has a fancy name in mathematical. These are called matrices where the rows and columns add up to 1 have been discovered in other contexts, and those matrices have a very, very lovely and fancy name. Can anyone guess what that name is? These are called,
Identity matrix.
no, they're not. They're called doubly Stochastic matrix, right? Where rows and columns, where rows and columns add each to 1, right? So that's what you, but anything else you do will either manufacture photons or will disappear photons, isn't it? So for example, if you did this 2 2 2 2, what will it do? It will conjure up all sorts of photons, right? You have 100 red photons and 0 in one channel, 0 blue in one channel. And when you try this, play this game, and you will realize that what it leads to is when you, so for example, if you multiply it by 100, 0, let us see what comes out. It comes out with 200 and 200. So what does it mean? Red channel, blue channel. They have now each 200 photons. But then if you say, where did that come from? Then, and if you look at the blue channel, 0, this is what it was. The blue channel had 100 photons, blue photons, right? This now becomes, oh boy, this also becomes 200, 200. Isn't it? So you can't use any matrix. If you use any matrix, your total photons will not get conserved. Right? So what do you do? How do you solve this problem? You need a doubly stochastic matrix where rows and columns add up to 1. But the whole question is, so how do you make a matrix doubly stochastic? Right? So given a matrix, is there a path to make sure that during the learning process, the matrix always stays doubly stochastic? The mixer never screws up the conservation law. That is the entire theoretical part of this paper. Manifold constraint means imposing a constraint, a conservation law constraint. Right? That is all it is. Right? So how do you, now the question is, what is this manifold business in this constraint? We understood in terms of photons, right? Do we understand it? We understood it in terms of photons, but where did this whole manifold, the geometry part, come in? That we will come to in second iteration over it, because the whole thing has a beautiful geometric interpretation.
So you're leaving us on a cliffhanger?
Oh yes, just stay there. Stay there.
Great.
No, because first the question is, I will address how do you make a matrix behave in the sense that we want, right? So let's say that you have a matrix. Let's throw some arbitrary numbers: 1 minus 2, 3 minus 4, or minus 3 plus 4 plus 1. I just threw in some numbers, integer numbers. Now you realize that, see, you're not allowed to disappear photons, isn't it? Subtraction is not allowed. Negatives are not allowed. So first thing you can do is, you can, if I do E exponentiation of H, if you exponentiate a bunch of numbers, what do you get? Only positive numbers, right? Because it will become e to the 1, e to the minus 3, e to the minus 2, e to the 4. This matrix is now positive matrix. So, well, we made some progress. That begins to look good. Now what do? We can do a funny thing, right? Let's say that we have numbers like, so let me take a bunch of positive numbers. 2, 3, 1, 4. Let me just take this. Now you realize that, let's look at row wise. You realize that they don't add up to 1, do they? So first we'll fix the rows and we'll pretend that the columns are fine, right? So what is 2 plus 3? 5. So we'll convert it to 2/5, 3/5. Then this will become 1/5, 4/5. Right? And now you notice that the columns don't add up to 1. So now, next time around, we'll fix the columns. Right? So we say a 2/5 plus 1/5 is 3/5. Right? So this time we'll divide it column wise. So 2, it will become 2/5 over 3/5. That will become 2/3, and this will become 1/3. Right? Likewise, 3/5 plus 4/5 is 7/5. Right? This will become 3/7. This will become 4/7. So now columns are working, but now the rows have gotten screwed. Right? But do you notice that they don't look as screwed anymore? 2/3 is 0.66, and 3/7 is 0.4 something, right? They sort of add up to 1. It's a better thing. So I repeat this now this way, right? So what happens is you alternate between fixing the rows and fixing the columns, and fixing the rows and fixing the columns. And if you keep doing this business, this is the famous, this is a famous technique discovered, I believe, in 1967 or earlier, and it is called the famous Sinkoff Knop algorithm. At the end of it, it will make a matrix into a doubly stochastic matrix. Big mouthful word, right? Doubly stochastic matrix. But what does a doubly stochastic matrix do? Basically, multi-channel signal, when it goes through that mixer, will still come out conserving the signal intensity, isn't it? That's all it says. That's all it will do to that. And now comes the beautiful part. Now the whole question is, now where is the geometry? Where's this manifold business coming into it? Right? Manifold business comes in through something called the Birkhoff. There's a lot of Sinkoff and Birkhoffs here. Oh, Sinkhorn. I apologize. It's not Sinkhorn. Yeah, no, that's what I was thinking. There are too many hops. Birkhoff, my apologies. Polytope. What in the world is this? Birkhoff polytope. See, look at this. If I have a signal that is all red and no blue, all red, no blue. This is a signal vector, right? On a channel. What happens if I were to multiply it with a, let us say I multiply it with a thing called 1100 P1. Nothing will happen. The signal will remain the same signal. Identity transform. So if the matrix was doing P1, it would become the old style residual, isn't it? But if I multiply by P2, which is the opposite of this, which is 0, 1, 1, 0, and you multiply 100, 0, you can convince yourself this will become 0, 100. So what will it do? No red, all blue. Right? You switch the red and blue from the channels, right? And now apply to the other channel, and what you will notice is that all of the photons have changed. Right? It's a complete permutation. You permuted the channels. Right? All the photons from here to there. Now, you would agree that no matter what you do, any mix, any reasonable mix that a doubly stochastic matrix will do, I mean photon conserving matrix will do, right, has to be somewhere in between this, somewhere between P1 plus 1 minus lambda P2. You can say either leave it alone or swap it or something in between, isn't it? You can convince, would you agree? These are the two extremes. So any transformation has to be in between, right? So this is what the research paper means when you say that the matrix is convex. It makes a convex transformation, because these kinds of transformations are called convex transformations. Or another way of saying it is that this manifold, which has only two endpoints, p1, p2, everything, any matrix transform that you have has to be contained, constrained in this, well, in two dimensions. It's rather trivial line manifold, because hey, a line is also a bona fide bedsheet, just has one thread in it, one blanket, right? So it is between these two lines. Now, if you go to three dimensions, you will realize that if you go to three dimensions, then your manifold is actually more complicated. There are there are 6 points in a four-dimensional manifold. So it's a little bit harder to describe. It gets complicated very, very fast, right? So that manifold with these points, what you're basically saying is there is a simplex, like let me just make a surface like this, that your H matrix will land you somewhere here, right? If those are all the permutations, P2, P3, P4, oh, I should have made 6 points. Sorry, P6, let me cheat, right? That whatever your doubly stochastic matrix would do to a three-channel signal would stay within it. And now you can generalize to four dimensions and so forth. Am I making sense, guys? Right. So this is called the Birkhoff polytope manifold. That is the interior space defined by this permutation matrices. Right. Signal per. In other words, any conserving photon conserving transformation on the signal inherently will be in the interior of this surface. Does that make sense, guys? And that is the geometric interpretation that you have. That so long as you stay in the interior, all will be fine. So that is the sort of the physics or the core theory intuition part of it. But then that is not where this paper ends. To create doubly stochastic thing is an old game in computer science. Remember, in algorithms, what do? If you have to optimize on two axes, you claim that it's already optimized on one axis. Let's fix the other. Then you fix that, and then you come back to fix the first one. You keep changing axes, right? So the Sinkoff part, the Sinkhorn part is straightforward. It's what you would expect to do. But this one is the Birkhoff polytope thing is very interesting. That it gives you a core intuition as to why this works. See, it has put a constraint on it. It's somewhat like in like your amplifier, you have a feedback loop or some constraint to manage the signal. It doesn't blow up, right? Now comes 3-4 big tricks that it says that, hey, boy, look at it. Residual channel just blew up. There's 4 times the signal now to remember in memory. So now comes the engineering part. Oh, by the way, as far as understanding this, is there any more question? So basically, guys, I've explained every theory part that this paper has, but I've explained using the two-dimension vectors.
Yeah. So I have one question here. So I'm trying to understand it from a vector subspace point of view. Is it like matrix transformations are linear transformations, right? So
that is right.
So how do we visualize it from that angle? Like, each P1, P2 are kind of subspaces. Can we say that?
No, P1, P2 are operators. No?
Operators. So they have vectors, right? I mean, each matrix has multiple vectors, correct?
Column vectors. But
Column
that's not the
vectors.
way you think about it. That's actually not a very good intuition. Matrices are operators that act on vectors. They transport a vector to another vector.
Right.
So here is one way to think about it. Imagine one axis. This is the red axis. This is the blue axis. You have one vector. Suppose I have a vector, right? This vector. What should I say? A pure red vector. So suppose this is a pure red vector, right? What will any operator do if I operate on it with a matrix A, B, C, D? On the red vector, which is, think about it this way, a red vector which is all red and no blue, what will it do?
Will either
It will take this
squeeze
to
or
some
stretch.
other place, isn't it?
Correct. Yes.
Right? So it will become something else. It will now become, let's say, this vector. What is this? It's a mix of red and blue. So the
Correct.
what matrices do, get this intuition right, because this is what is more universal than whatever you have learned. Geometrically, matrices are operators, right? Or think of it as Uber drivers. They will take a vector from here and put it somewhere else. Square matrices will literally take you somewhere else.
Hmm.
Are we together? That's what
Yeah.
matrices do, right? So think of me the whenever you see a matrix, think of it as a operator. It operates on a vector and takes it somewhere else, right? And it gives it a different meaning. So the green vector now has mix of both red and blue now. That's the way to think. Okay, somebody else was saying a comment.
So if I wanted to say P2 was anti-clockwise rotation, right?
That is right. That's right. That's right. P2,
90 degrees.
no. It's a swapping. Yeah, it just swaps it. Like it makes the red blue and the blue red. Like basically, it will give you this one, right? It's a swap. It will swap the axis. It's just a swap of the axis. P2, Dilip.
Yes,
So
no
Dilip,
worries.
that's why they're called permutation matrices. They just change the location. You permutate the axis. See, moving all the photons from the blue channel to the red channel, and the photons from the red channel to the first channel, blue channel, is the same as basically interchanging the channels, isn't it? That is why in classical math literature you call them permutation matrices.
Right.
Elisa, go ahead.
Yeah.
One question I have is, the two questions. The first one is, it's going over Birkhoff polytopes and other very interesting concepts. So what would be good for our homework, like before the next session, so I can be prepared with these? What would you suggest, the top three to really understand for these concepts?
Elisa, so I'll make a broad statement, and unfortunately, it's a sweeping statement.
Mm-hmm.
See, the inadequacy that all of us computer scientists are facing at this moment when we deal with AI is the education that we got in AI, in computer science, which was mostly discrete math, big O notation and all this. How do you balance a tree and all of that, and graphs and stuff like that. That education, that mathematical literacy doesn't help us in the world of AI as much, because AI needs you to know a field called differential geometry. Right? It's the study of manifolds and fiber bundles and forms. Even the definition of vectors that we were taught in basic engineering is wrong. We were taught a vector classically in all the books of engineering is still written as something that has a magnitude and a direction. Mistake starts right from there. A vector not only has magnitude and direction, it has an address. It must be located somewhere, because a same direction and magnitude vector here and another one there are two different vectors entirely. Right? So, but on the simplifying assumption that whenever we give a vector with magnitude and direction, we just implicitly say its home address is the origin, right? Then it has sort of worked. Now there is a need to re-educate or to educate ourselves properly in this field of differential geometry. So what people are realizing is that this field of AI, and that is why, see, if you read this paper, today's paper, the Manifold-Constrained Hyper-Connection, and you go back and read the papers that are coming out from the top research labs, Jan LeCun's papers, Jeffrey Hinton's papers, DeepSeek, Google Brains, and DeepMind, and the FAIR of Facebook AI Research Group, all of these, you will notice that they buried in there are deep mathematical intuitions. What they do is they think mathematically, and that is my hypothesis. They erase the math and they write it then, after having erased most of the math or just condensed it to the appendix. What it does, what it makes it hard for us, is to then reconstruct the bridge They have erased the bridge because engineering papers tend not to give you the underlying intuition or the explanation. They erase it.
Yes, Asif, absolutely. I've been looking at differential geometry for years, so I absolutely agree with you. For this paper, though, I'm just very curious on what would be good for us to look at specifically, like which ones.
Oh no, this is it. There is no specific thing. See, what will happen is no matter how much you learn, whenever you encounter a paper, you will find that your knowledge has some holes. Now, you can't go and learn. Math is a vast field. You can't go learn everything. Like in my own case, I was aware of the syncon, the NOP algorithm, because, in matrix, if you ever do a course in matrix computations, you go through the grind of all of this. Then I knew what it meant. The Birkhoff polytope, actually, I had forgotten. Now, but then I have one advantage over the regular computer science people. I used to do, in a past incarnation, quantum field theories. When you do quantum field theories, well, the foundational math is differential geometry, right? Homology, cohomology, and all this, and field theory. What people are realizing that AI, so that is why for me it's I have an undue advantage in some sense. Because it's as the field is moving in that direction, I'm sitting there and saying, welcome home. Right? So,
So should we? Okay, so what I'm hearing is the Birkhoff. We got to look at that, and we got to do the double stochastic, which another friend suggested, and then so that I'll look into those two. So for everyone, I invite you to join me. And then the other question I have is for this paper. I'm curious what you think the potential is here. Do you think we see
vast
this
potential.
like okay, do you think it's actually like currently we're able to get there with implementation of this?
Elsa, I have a very strong feeling, and I have no doubt now that see these ideas that these guys are coming up with, every guy, every single large scale model builder looks at this and says, okay, in our next version, we need to incorporate this. It's as simple as that.
Okay. Thank you for your opinion. That's very interesting.
Yeah. So I'll come to that. So now I'm coming to the engineering part of it. So Elsa, there is no doubt people are not exaggerating when they see you see some hyperbolic statements about this paper. The DeepSeek has once again completely transformed the transformer or make a there'll never be I don't know what hyperbolic statements are there. Well, those statements give you a lot of viewers on YouTube, so I can understand why people market it like that. But there is a grain of truth to this. I would be very surprised if somebody does not use it next time they build a transformer, the next time they build a language model. These ideas all add, see, the good thing about engineering is ideas come from everywhere and everybody keeps incorporating all the ideas. Right?
Very interesting, yeah, because when I ran this by an AI researcher, they were a little more skeptical, but it sounds like you are seeing the sky with this one. So it's very interesting.
That is right. See, everything contributes. Everything contributes. And it adds up. Whenever a next generation language model is built, dozens and dozens, if not hundreds, of new research papers have contributed to the way people sit down and build the next version of a language model. It's always true. It's always true. See, the companies compete, the researchers collaborate. That rule has forever been true. Researchers collaborate. And in a way, good researchers, they stay away from geopolitics. Let the good ideas come from anywhere. Right? So now I'll talk to the engineering aspect, which will be a short discussion. I'll talk about 3-4 tricks in engineering. Yes, go ahead, Sushant. There was no, instead of being constrained to stay within this good region, the matrix could be anything. So it could conjure up photons, it could make photons vanish. Because a non-doubly stochastic matrix, if you really think about in terms of photons, what is it doing? Magically, the signal is going through the mixture and magically the signal is getting amplified. More blues are coming up, right? Somehow. Right. So that was the problem. See, a lot of these things, they look very abstract. And to Elsa's point, right, you can go and read doubly stochastic. And then you keep scratching your head. So why does it matter? Isn't it? And then they throw this uh, the Birkhoff polytope on you and manifold constrained. And you're even more confused. What just happened? Right? So as I always say, right, dumb it down. Start with very simple, small steps. Start with 2 dimensions and start explaining, understanding things from 2 dimensions. See, when I reduced it to 2 dimension and a physical intuition of photons, doesn't this entire paper look obvious? Isn't it? What they are saying is they are telling their predecessors, dude, you're magically either creating photons or stealing photons. Right? Let's stop doing that. And that is the gist of to say it is manifold constrained. That's all it is. Right? And that is the purpose of a doubly stochastic matrix, right? What happens when you balance the rows and columns to one? You literally, it's a conservation law. Yeah. So but you don't see those things. Actually, they use the word conservation of intensity somewhere. So you see, it is the little clues somewhere in the language. If you read carefully, right, you get a clue to how the researchers are originally thinking. Right? But papers are written in a very dense and formal way. And these people have used really long sentences quite often that requires a lot of background to get the hang of. But you can get the hang of it. Right? So now I'll come to the engineering aspect of it. So here is a problem. It's called the memory wall. So here is the big problem with the GPU. GPU's nature has 2 problems. It is compute rich, memory starved. Not just memory poor, it is memory starved. In a GPU, there are 2 kinds of memory. Memory is the register. Register where? Register of each of this little cores. Right? Core register. And it has the HBM, this much slower high bandwidth memory. And Sushant, you work with this hardware, so you know it, right? So now the trouble is high bandwidth memory is nevertheless way, way, way smaller than the register speed, isn't it? It's much slower than that. But GPU's basic nature is as compute rich, memory starved with horrendously slow data traffic. Data traffic. The intercore, if you want to move data from this GPU to another GPU, it is a catastrophe. The cores will just sit idle. So I'll give you a basic thing, guys. Today, when you go and buy a RTX 5090, if you look at the number of cores there, and if you look at the number of a cores in a very expensive, so RTX 5090 is MSRP 2000, though nobody is able to get it below 3000. But if you go and get that Blackwell 200 from NVIDIA, and the moment you say Blackwell 200, they say, all right, let's start talking at 200,000. I'm kidding. But it's horribly expensive, right? What is the fundamental difference? The Blackwell 200 is actually just 2 of the chips that you see in a 5090 in a butterfly configuration with a bridge in between. I'm oversimplifying it, but that's pretty much it. So why is it not costing 4,000 instead of hundreds of thousands? Question worth asking, isn't it? And the simple answer is that 2 things. When you put 5090s on your workstation and let them interconnect over PCI bus, it's slow connection. And that connection is really very slow. The B200s are interconnected using their NV links and so on and so forth. Very, very fast connections. The other thing is that they have a lot more HBM, what is called high bandwidth memory, but I will just simplify it as VRAM, virtual RAM. Actually, 5090 doesn't even have HBM. It has a much cheaper version, consumer version, called VRAM, the GPU RAM. Yeah. So memory is very expensive.
Same as HBM?
And no, it is the memory resident in the GPU.
Okay.
So now it is, and the horrendously slow thing. So that is the problem that is part of the memory wall. So see, what happens is that If it fits into the memory of a register, you have a win. You have a cache hit. You have a literal hit. So think of it as what you would call a cache hit, but think of it as a register hit. If not, and you have to go to the HBM, that sucks. If you have to go over the data traffic lane, get it from the other GPU, oh good grief, right? You might as well, it's like, taking a flight from here to Europe, right? And getting buying some things there and coming back. It's very, very slow. So that's the problem. Now what happens is, the more load memory you use, the less likely it is to fit in one GPU. So you will have to have model sharding, right? And therefore compute sharding and all of that. Now imagine that a model is here and here. If you use 4 times the memory, you're likely pushing it into multiple GPUs now. Then how do you solve that problem? Then you also have to remember that in the forward pass, input and output through a layer in out are both remembered. Why? Because you say that you remember the gradient. You will have to know the function gradient, the local gradients, derivatives here. You save that. But not only that, you save the del square, quadratic gradients, etc., etc. At the overhead, you take basically, right, a full model training takes almost a 16x overhead. Right? So any memory, excessive memory you use at training, at inference time, it's okay. At training time, you are basically in trouble. Right? You will need lots of GPUs, you'll have bloat. So how do you solve this problem? The first trick they use, so trick number one, they say, hey, forget, we won't store. So what happens if I don't store input, output? I'm just looking at the residual lane. Suppose I don't store it, right? So then what happens? When I'm doing the back prop, what I will do is, because I need the output also to be able to propagate the gradients back, compute the gradients, what I will do is, if I don't store it, means in the back prop, I'll have to do the forward pass and then be able to do back props in that layer, isn't it? I would have to compute this and then do this. But they say that is fine. Compute is cheap. Memory is expensive. So I'm just not going to store it. Right? During the back prop itself, I will recompute it. Right? Recompute the factors, the output, and then move forward with it. So this is the recompute. So this is what I would call this is the capacity hack. What does it do? It significantly lowers the cost of having 4 channels. Are we together, guys? Right? It significantly lowers the cost of 4 channels. The second trick that it uses is a kernel fusion. Because remember, the biggest problem in neural networks is, in the compute part, is that what happens is you compute something, you put it in the HBM, then you bring it back, again recompute, again put it back, then again bring it back, again. That is even when you are local, you're not even going across the GPU. So there's the trick number 2 that they use. Number 2, this is your kernel hack. The kernel fusion. I will call it the latency hack because it addresses the latency aspect. It mitigates the latency. Because see, this whole back and forth between the register and the memory introduces vast latencies. And of course, any kind of transport across will introduce its own hell of a latency, right? So what they do is, they say that there are multiple steps that are needed. Like you have to normalize the signal, you have to do the multiplication with this H, the matrix, etc., etc. And then we forgot the layer part itself. Remember the actual signal that modifies that. Let me go back. This path. Remember that there is this path also, right? So they say, let's do all of it as one single operation in the registers. Right? The fuse. This is the kernel fusion. All of these operations, let's do it together. Right? And when you do it together, that brings about low data ones, mix, normalize, off ramp, right? Right results. And wherever possible, the hot data, keep it hot in the register, right? Bypassing the slow memory bus. That's an important trick to use. And then there is a third trick that you use. What is the third trick you use? The third trick that you use is there a fourth trick? Oh, no, actually 3 tricks. So the trick number 3 that this paper uses is, it is called the traffic control hack. So the problem is, the model is split across multiple GPUs. GPU 1 must wait idle while sending data to GPU 2. Yeah. Does that make sense? That is the horrendous latency, right? The biggest latency is, oh gosh, I'm waiting for data. And you sent it to GPU 2 to do some computation, it will come back. So then you use a trick which is very common in operating system. In operating system, what do you have? A scheduler. And what does the scheduler do? If a process makes a block IO request or something, it will just park it and in the meanwhile start process doing other jobs. That is your trick number 3. It has an internal scheduler. What it will do is, it will say that, see, all of those kernel fusions that it has to do and all of the mixer business that it has to do, multiplying and figuring out, it will first do this. It will figure out what I need from the other guy, right? Make a request to the other guy. But in the meanwhile, it will use that idle time to quickly start doing the real computes, so that the cost of the real compute basically collapses to 0. You see that, right? Because if the biggest latency is from the inter-GPU communication, why not use that shadow time to do this compute so that the cost collapses to 0? It is not visible. It was in the wait time of that. So that is the trick number 3, which is the traffic control. So there is a subtlety that comes up. What if the other guy, it's basic RPC, right? You make RPC and go do other things. But what if the other guy comes back sooner? What you do is, you preempt. You take the result and then quickly still do the computation. Right? That's all you do. So because of these 3 tricks, the paper just incurs a 6 to 7% compute overhead. And now I'll get back to the paper and I'll show you what wonderful results it leads to. Right? So guys, have I given you enough foundation to understand the paper now? Right? So let's read the paper now, and you'll find that it's a very quick read. Right? Does this make sense, guys? The leftmost is the classic residual. What happens to the signal on the side channel? It just goes through, isn't it? But with the hyperconnection idea that the predecessor gave, it came back with 4. Do you see this 4 channels? Right? There are 4 channels of signal. And right away, you multiply with HRES. This picture has a little bit of a thing to do, but anyway. And then what you do is you collapse the signals into a single signal, because why? Your traditional, attention layer or whatever it is, or feed forward layer, it is expecting a single signal. So it doesn't even know that the 4 signals are there. It goes through, there's a pre-mapping, there's a post-mapping that will now split it back into 4 signals, right? Back to 4 signals. See, you notice that this is a single channel, right? Single channel comes out, it gets broken up into 4 channels again. And this highway, here you just go to the HRES, this mixer. This is the mixer I was talking about. And it will produce an output which gets merged. So what did this paper really do? This paper, at the end of it, if you compare these 2 diagrams, do you see that they look uncannily the same? Unless you carefully observe, you can't tell what the difference is. So let me highlight the difference. Do you notice that here there is HRES? But what this one has done is, it has applied the doubly stochastic constraint on that, right? Made sure that the transformation stays within that Birkhoff polytop manifold. The ant doesn't crawl off the blanket. Are we together? That's the only difference it has made. Everywhere you'll notice that other than that, we are all in the same thing. But that thing is the crucial thing. Because interestingly, this is not hacking. This is deeply understanding what is happening and then doing it. Right? Now, this is exactly what I told you, that the original signal is there and then you are just adding a little bit more to it. Right? But when you do it with this H matrix, the problem is you have the multiplication that we talked about. Do you remember that? All the matrices multiply of the previous layers. They start getting multiplied in the residual channel.
Yep.
Now, yeah, that is it. That is it. I mean, once you get what I just explained, the rest of the paper, in my opinion, should be a very easy read after that. And these are all the standard transformations that you see pre-post. The significance of this is, look at this. This is the result. If you don't do, look at this. Compared to loss gap, how much different if you don't do this, if you just do hyperconnections, then your loss is the prior version gives you significantly higher loss compared to the baseline, compared to the best method, their method, mHC method. Likewise, if you look at the gradient norm versus step, remember we talk of the gradient exploding, right? So it is saying that with training steps, like each training step, what do you notice? Gradients stay well behaved, right, in the mHC. But here, do you see that the gradients keep moving up and down, right? But more telling is this thing. When you look at the single layer mapping, this is the max gain. Max gain is what they're saying. Take the H matrix, add the columns and add the rows. Right? What does it add to? What should it add to? 1. But what is it? What happens is that single layer mapping is still that. But here is the problem. Look at, without using it in the forward signal, just the hyperconnection without constraint, it explodes to almost 3,000 times or 5,000 times. So that is your signal exploding. This is, the mixer is somehow conjuring up new photons, isn't it? Lots of new red and blue photons. But if you look at this, what is it doing? Look at this regime. It's staying very well behaved, isn't it? That is it. Now, this is the compute operation, how much it adds to it and so forth. So now, this is what they're saying, that make sure that both the rows and columns add up to 1. So what happens is when you keep doing it, it will never be exactly 1. But in 20 steps, it will become close enough. Right? We already saw that in 2 steps in our example, it was already beginning to get better. Now comes the engineering part, 4.3 onwards. Kernel fusion was 1, right? Not keeping the things for other. So they go into the details of how much each step costs. Those details, actually, you can look into the recompute. So they are saying that we'll recompute the output, right? So we don't have to keep storing them. So that saves them. It's only for the residual channel. They leave the main channel, the main architecture the same. And communication computation overhead for mHC. So this is where they talk about the fact that, we'll steal that shadow time to do even those computations. And when you look at it, if you look at this, absolute loss gap. So you say that compared to the loss of the vanilla language model, which is this line that you're looking at, the loss of the light blue line is much lower. So the predecessor, which used hyperconnection, was already doing better. But observe this gap. Manifold-constrained hyperconnection does actually better than hyperconnection, even though you impose the constraint. It isn't that because you impose a constraint, it starts doing worse. It actually does better. And this shows, and when you look at the gradient norm, it's magic. Look at how well it flows. Right? The bright blue line, which is this, is well behaved compared to the light blue line, which is for the hyperconnection one, which is so ill conditioned, right? It sort of keeps moving up and down. And so what you show is that you have a well-governed system. But now let's look at the benchmark. These are the different benchmarks. You can clearly see that in most benchmarks, except one, here, so I'm just making circle around the best values. And this is the thing. So you realize that this new architecture beats the baseline everywhere. It may not beat the HC for math, right? But it beats the baseline. I mean, it's just a difference of 0.4, but it beats the baseline dramatically, isn't it? So what is it? The big lesson is you can improve, you can make a better model, not just by making it bigger, neural scaling, but by being smarter about the architecture itself, which is the core message of this paper. And then it goes on with more. If you look at the layer level composite mapping, the Amax gain magnitude across, see, it stays within a very tight envelope. 1.5 is nothing compared to 5,000 that the unconstrained one achieved. Where is that picture? Yeah, look at this. This one, the unconstrained one, the Amax was like 5,000, close to it, right? 3,000 or 5,000 times amplification, which is basically exploding signal, right? Whereas here, the maximum explosion that ever happens is by a factor of 1.5, which is pretty tame. Look here. Look at the 1.5 here, right? So actually, this makes more sense when you compare it with many pages before the other diagram. Then you realize that, wow, right? What a tremendous. Actually, I wish they had juxtaposed them in the same graph, because then the difference would be immediately visible. Right? So, well, this is it, guys. This was the paper, and I hope you had fun with this paper. Go ahead. Did it reduce the number of layers? Yeah, I got a question here in the audience for those of you who are remote. The question from the audience here is, did it mean that you could use less layers? See, there are two ways of looking at it. You could say that it gives me the capacity to make the model smaller and still get the same performance. Or you can look at it the other way around. For the same size model, I now get a much more capable model. Right? So you can look at it both ways. For those of you who are remote, any questions, guys? I hope it's a dense paper, but I hope I gave you some color to it. Or I gave it some color to make it easier.
Other than double stochastic and the other one, the Birkhoff, I think. Any other
Birkhoff
concept?
polytope.
Yes, that one. Any other ones that we should
No,
look at?
that is it.
That's it? Okay. All right.
That's it.
Good to know. Thanks.
We all are here. I mean, it's such an interesting paper read. I mean, we could not just let off. So yeah, we all, 27 of us are here remotely.
Oh, okay.
Yes, we're all on the edge of our seats. Absolutely.
It's a wonderful paper, isn't it? And at the end of it, all you realize is what people were finding that somehow good idea, but they didn't know how to make it work. These guys figured out how to make it work, but also make it work without paying the piper, without paying in terms of huge compute cost escalation. In fact, there's almost no compute cost escalation.
So we can use this for our some simpler networks as well, right?
This idea is applicable to anything.
Yeah.
I would say that going forward, the direction should be that any network that has a residual should now have the mHC residual. As simple as that.
So, as if given for this source code for implementing this somewhere.
In their case, yeah. See, DeepSeek has a habit of releasing all the source code. I don't know. If you go to the DeepSeek GitHub, my feeling is you'll find it there, but I'm not sure. I didn't check it. But they are one of the most open about their research. Check it out. I don't know, actually. I don't know the answer to that question.
Sure, we will.
Nice to see you here again.
Hey, Asif, this is Richard. Just one comment. So it seems like this is like another way of doing normalization at the residual layer. We did previously normalization at the logits layer for probabilities, and then with muon in the linear transform layers, while normalizing the eigenvalues to unit radius. And this is like another layer of normalization in the residual stream, which is not being done before.
Think of it. Though I think of it as more as signal conservation. You can think of it like that. See, Richard, here's the thing. The deeper question to ask is, why did HC, the predecessor, succeed at all? Right? And the reason they succeeded is, the fact that at each layer signal was getting normalized anyway, nah,
Made
Yeah,
sort of
that's
dampened
a
down
good
the
point. Like the
situation.
comparison between the two, the previous thing was also working, right? It's been working so far.
it was working for only so many layers. So in other
Uh-huh.
words, because of RMS normalization being there, what happened is that the blow up happened only when you made deep layers, right? But
Okay,
it was
great.
still
Yes.
working. But the problem was that sooner or later it blew off, right? And that needed to be fixed. And these people fixed it.
Okay, so this basically allows you to go almost unlimited depth because
Unlimited depth now. Yeah,
that's the key outcome. Okay.
that's the key outcome.
I missed that photon analogy, but I suspect it was about conservation of energy. That you
Conservation
were,
of photons.
okay. Some conservation law in play, which is an analogous to what we're
Yeah.
doing here.
See, I was giving the see when people use the word doubly stochastic matrix,
Yeah,
and
it's
then
basically
Birkhoff,
conservation.
yeah,
Birkhoff polytope, then you begin to wonder what exactly it is. But the moment you think in terms of simple physical intuition, you know that you're just saying conserve the intensity of the signal, right? Conserve the
Exactly.
number of photons. And it becomes then, frankly, far more easy to grasp. That's all you're doing.
Very helpful. Thank you.
You're welcome. All right, guys, now I'll close this. If anybody has any thoughts, please ask. And I apologize if you find that I was mistaken at any place.